I mean, essentially, the plan for today is really quite simple. I just want to cover magnetostatics. So I'm kind of happy because we're following the original plan of the course. The original plan of the course is that we handle everything, static before the midterm. Now that means that next week I'll be doing magnetostatics in matter. Officially, this is going to be also exam material for the midterm, but of course, since it's going to be quite fresh material, that's not going to be the main part of the midterm. The midterm is going to be just mostly about the things we've been talking about up to now and what we'll talk about today. Now, I've also had questions from some of you about the precise compilation algorithm for the grade, and I was convinced, or at least asked to consider making the midterm like if you want count for you only if it's positive. Yeah, so I mean just to make that clear, that's what's going to happen. So technically, you can pass the course by just sitting the final and doing well at the final. Okay, but doing the midterm is just giving you points in the bank if the bank happens to be in your favor. Okay, I mean, of course, I would say that if you're not doing well at the midterm, then alarm bells should be ringing and you should take corrective action before the final. On the other hand, if something happens, then the midterm is not going to be fatal to you. Okay, so what I'll try to do also about the midterm is maybe complete the set of things you should know for the midterm. I'll also do that very, very clearly for the final, just a bit before the final. But hopefully, you can find your way around with what we have. So typically, the exercises we give you, which until now, many of them have been like self-made. Actually, last week I gave you more Griffiths-based exercises. This week I'm also doing that because a couple of the assistants are actually away on other social events where they get an update on the latest viral infections to go through the world. The exercises that we've given you until now, because they were self-made and things, sometimes they went a little bit above the material or a little bit aside the material. You should really, when you look at the exercises in Griffiths, feel that you can do most of them. Some of them are marked with little exclamation points and things, and are more difficult, but you really should feel that you can do essentially anything in there because it's quite conceptual. And I was actually talking to my assistants this week a bit. We always do a bit of a kind of, well, I shouldn't call it like that, a post-mortem of the exercise sessions. So of course they're not very well attended, so that's a point of concern. But once again, so you're adults, you do what you want, or yeah, and mostly here, I guess I'm talking to the people who are not here. I was like reminiscing on when I was young and I was, in your seat. I personally felt that it was very important for me to really understand the theory before I started working on the problems, because I would see that many of my fellow students would rush through the theory thinking they understood and then immediately start on the problems and get blocked. And it's not by spending a lot of time being blocked on problems that you unblock yourselves. You unblock yourselves by going back to the fundamentals. The fundamentals are relatively straightforward. If you understand the fundamentals, typically, at least you know how to start on a problem. So my suggestion to you is that you make sure you kind of know the fundamentals like that, and if you want to test whether you know the fundamentals, you kind of go through the list of problems. And if you know how to start with a problem, that's a very, very good sign. If you don't know how to start, then that's a bad sign. Now, problems, of course, sometimes have little technicalities that are specific to that problem that you need to solve, but that's not the point. The point is to get the big picture. The point is to be able to use the fundamental equations to really understand the concepts. And that agreed, it's good to do exercises, but doing just exercises without doing the fundamentals is not good enough. Okay, so I don't know if this is useful at all to you, but anyway, just a little tip, because it's also something I noticed quite a lot. In the Netherlands, most people spend more time on the exercise sessions without having properly studied the theory before, and that usually leads to, long-term handicaps. So be careful with that. But okay, enough pontification about these things. Again, you're adults. You can handle all these things, you know, in your favorite way. Okay, so I mean, again, we do like one theme per session. Last time it was electrostatics and matter. I mean, I know that you're still maybe struggling with quadrupoles and things like that, but again, this is like a deeper detail. I would like to keep the compartmentalization quite tight. So today, indeed, we're going to focus on magnetostatics. Okay, so how does this go? In a sense, the word statics here is a slight misnomer because as we'll see, we will be talking about currents. And there is, if you want, nothing static in a current. Things are moving, things are not, you know, time independent. However, perhaps a better synonym that could be used here is the concept of steady things. Yeah, so if you have a steady current, it has no time dependence associated to it. Therefore, the way it looks does not depend on time. So despite the fact that it's a dynamical thing, it's not a static thing. It is a steady thing. Okay, so that's the kind of spirit in which we'll be doing the magnetostatics. So I want to start with a few very, very basic things that, of course, you already know, just to make clear that everybody's on the same page. So the fundamental thing that essentially microscopically it's all based on is the Lorentz force law. Okay, so that you'll remember. So the force vector acting on this, acting on a particle, the magnetic force is just the charge of the particle, the velocity of the particle crossed into the magnetic field at the position of the particle. So this is appropriate for a point charge, right? Where we know exactly where to evaluate the field. It's at the point at which the particle is. You can ask yourself, is this like a proper quantum mechanical here? Because in quantum mechanics, I cannot know the position and the momentum of my particle simultaneously. Okay, you see immediately you're asking too many questions. This is not a course in quantum electrodynamics, but I just pointed to you a little subtlety here that can occur when you start doing quantum mechanical things. But for us, the world is simple. We're all classical, so this is completely well defined. Okay, the total force, so in presence of an electrical field, yeah, then the total force would just be Q times E plus V cross B. Okay, so again, this is something that you know quite well. One of the examples is the cyclotron orbit. So what is that? I have a magnetic field going, I don't know if you've got this convention here, so if I write it like this, it's going inside the page, right? Because you see the butt of the arrow, and the arrow has these four little, feathers to direct it. So if I've got a magnetic field pointing into the page like this, I've got a charge Q greater than 0. The amplitude of the field is just B. So the idea is that the motion is a circular motion. Circular, seriously. Where the magnetic force cancels the centrifugal force. Okay? So, mag force cancels centrifugal. So that means that my QVB, that's the amplitude of the magnetic force, is just mv squared over r. And that tells me that essentially the impulse of the particle, P is mv, is just qbr. And the frequency, so the cyclotron frequency, number of orbits you do per second. Yeah, the kind of angular velocity of this thing, 2 pi v divided by 2 pi r. So that's just qb over m. Okay, so you see this is kind of cool because for a known magnetic field, if you see a charged particle doing circular motion like that, you can determine the ratio q over m. Okay, so that's really something that's used in experiments in bubble chambers, for example, where you see traces of motions of particles. You can really work out these fundamental ratios like q over m. Okay, so this is all very simple. This is all stuff that, that you know. Now, of course, a single moving charge is something which is not a steady current, right? So we're more interested in charge distributions that are in motion. So let's just define some of the things that we're going to use as far as currents are concerned. Okay, there are some examples in Griffiths. I mean, of course, you can have just a wire with a current in it, and if the wire has a certain shape, there's a certain velocity of the charges in there, so you know exactly what the current is in there. In general, we're interested in like charge distributions that can move about. So let's say you're kind of an advanced researcher and you're looking at motion of charges in a tokamak. Yeah, you know these tokamak things that try to do fusion in these things. You have these super hot plasmas. You're trying to generate collisions in there to create fusion. Of course, the currents that you have in there are absolutely gargantuan. So, but the way you describe them is essentially by having clouds of charges moving about with local, well-defined velocities. So the kind of preferred notion that we have of currents here is that they come from patches of matter with certain charge densities moving at certain velocities. Okay, so so what do we mean with that? So you know the flow of charge. So if you have a charge density rho moving at velocity v. Okay, v is a vector, rho is a local scalar. Okay, it defines this this current density, which is a vector j, which is just rho times v. Okay. Now, if you take a certain surface S, okay, then the total current going through the surface so the total current going through the surface is just I, the integral over the surface of your surface area, dA, with this J in there. Okay, so then you're really talking about number of charge per unit of time that goes through this thing. Okay, whereas J has units of charge per unit of time, but also per unit of volume, because I've got this. Okay, so we can write an extremely important equation from just basic considerations here. If we have a closed surface, what we can do is use the divergence theorem, and that just tells us that we can equate this surface integral here with the volume integral of the divergence of this object, the current density. Okay? That's just a straight application. But of course, charge is conserved. And because charge is conserved, it means that essentially the current going out of this volume, as exemplified by this surface integral, which we've rewritten as this volume integral, this has to be the time derivative of the total charge enclosed into the system, which is just the integral over the volume of the local charge density. Okay, so essentially we're kind of just using a symmetry of the problem, which is that total charge is conserved, and we're translating it into a local equation. I mean, we're kind of not yet at the local thing, but we'll get there in a second. Okay, so this here I can simply rewrite as the integral over my volume, d tau, of now the, I'll write it as the partial derivative with respect to time of rho. Okay, it's now partial derivative because, of course, rho is also a function of the spatial position. Okay, and because the integral converges, I assume that the charge is finite here, I can actually invert the operations of taking the differential and of performing the integral. Okay, so I can move the differential into the function like here. Now, the crucial thing is that this has to be true for any volume V. And that means that the only possibility left is that the integrands have to be equal. Okay? So because I can move my surface of the volume where I want it, this equation holds everywhere for any volume V. Okay? And therefore, the only way that this is always going to be equal is if the integrands themselves are equal to each other. And that leads to an extremely important equation, which is the continuity equation. Which tells me that the divergence of the current density plus the time derivative of the charge density has to be equal to 0. Okay? What goes out changes the charge, what comes in changes the charge as well, according to this equation. Okay, so this is like a super important equation that you should essentially know by heart. Now, we've applied it, of course, to like currents, density of charge, but a continuity equation is completely universal. You can apply it to lots and lots and lots of things, right? You can apply it to a fluid, to gas and things, if you measure the number of atoms somewhere, whatever density that you have, for which there exists a conservation law, namely a quantity that is not dependent on time, in this case here, total charge. Okay? You can write such a continuity equation because if the global thing is conserved, then locally, if you lose something, it has to reappear somewhere else, or it has to flow out. Okay, and that's all that this says. Now, you might find that very, very, very simple, but the things I just told you contain a number of like super profound concepts in modern physics, in 20th century physics, even 19th century physics. So what are they? First of all, the existence of conservation laws. You're familiar with, of course, conservation of energy, because we've told you it was like that. Conservation of total charge, that's just an experimental fact. Okay, we have it like this. But conservation laws are typically related to what are called symmetries. You might know there was this wonderful lady called Emmy Noether. Have you come across Emmy Noether? Noether's theorem in classical mechanics? Okay, so who was Emmy Noether? She was an absolutely brilliant German mathematician, and she never got a job because she had like one fundamental failure at that point for academic work, which was that she was a woman. Fortunately, things have changed a bit, but she came up with the most profound theorem of mathematical physics that we have in our possession, and that's essentially the relationship between a symmetry and the presence of a conservation law. Okay, so if you have time translational invariance, you will get energy conservation. If you have rotational invariance, you will get angular momentum conservation and lots of other things. And in what are called gauge theories. If you have like gauge invariance, you will get indeed like charge conservation, things like that. So, so that's the first comment. So Emmy Noether, actually they just renamed the university in Göttingen in honor of Emmy Noether. I think that's great. I think it happened like yesterday. So pretty cool. But here, essentially one more comment about the profundity of this thing. It's that we have a global conservation law, namely that charge is globally conserved. But what we have achieved here is a local continuity equation. Okay, so there's like an extra little element in there. Why have we done this? It's essentially because we have written the currents here in terms of changes of like local quantities. It wouldn't necessarily have to be like that. You could have some non-local physics in there, but that would be more complicated. Okay, but that's the kind of hierarchy of things. The existence of a symmetry means the existence of a global conservation law. If you make some assumptions about locality, you end up with a local continuity equation like we have here. Okay? So sorry for like going off on a tangent like this. I just think sometimes it's important to recognize important concepts like that. So for example, in quantum electrodynamics, you've got some local gauge invariance that you're putting back into the theory, and that gives you all the equations that you need in order to solve stuff. So these continuity equations, they're extremely important. They're also valid in a quantum mechanical sense. So you'll see them popping up in a number of different circumstances. Okay, so that's for the continuity equation. Now, in the notes, you have a few examples of, there are different situations. You can have a volume of charge that's moving, defining the current. It could be that your charges are confined to a certain surface, so you would have like, a sheet of conducting material in which a current goes in a certain direction. You could have just a wire in which it's just like 1D movement of these things. I'll let you look at the notations for these things. In the exercises, you'll recognize some of these things as well. And I think, you've already discussed these things, right? So I guess the continuity equation is something that you will already have seen in the first course. Did you or did you not at all? No recognition? Yeah? Okay, but now you've seen it anyway. Okay. So that's the first important element. Now, we started electrostatics by talking about Coulomb's law. Essentially, Coulomb's law told us what the electrostatic force on a point charge was. In the case of magnetic forces, there's a similar, kind of similar fundamental law, which is the Biot-Savart law. Okay, and this is actually an experimentally established law. Of course, back then it was just a question of doing some measurements with things. So these two French guys actually performed that, and we'll discuss a bit what it is. So what does it give us? This gives the B field generated by steady state currents. Or I'll just write steady currents. Okay, so what I mean by that is that in magnetostatics, what we will take is that locally the charge will not change. There's no time dependence in there. And that means from the continuity equation that the divergence of my current density is just 0. Okay. So Biot-Savart tells me that if I want to have the magnetic field at a certain position R, what I have to do is there's a proportionality constant. We discussed about these proportionality constants at the beginning. You remember this vacuum permeability that was just redefined in the International System of Units. Okay? So what do I have? Let's say that I have a line integral over a certain configuration, and then I've got the current cross r minus r prime divided by the usual thing. So it goes like 1 over r squared, okay? So I write it like this. It's vector r divided by norm r cubed, so it goes asymptotically like 1 over r squared. Okay, so this is really just something that that is given to you if I have a certain wire with a certain current going into it, like this, and I take a little section dl here, then I want to measure the contribution to the magnetic field at this point coming from this little segment here, then this is just mu 0 over 4 pi with this factor here. Okay, so if I give you a certain configuration of currents, a certain pattern of, you know, maybe wires that that create the magnetic field, then you can use this directly to compute it. Okay. So, I mean, I don't know if it's kind of useful to make examples of this. There are, you know, some simple examples in Griffiths. Where he takes so there's example 5.5, which takes it for a segment of a wire. Where is it? B from wire segment. Okay. Again, I will kind of let you look at this because I think you've already done these calculations in the first course. It was like in the material that was in there, so you should be able to do these integrals. Look at this example 5.5. You just have like a wire like this, and then you're considering some current in there that goes like this. And you're asked to compute the magnetic field at this point R here coming from this current there. Okay, so you can just compute it. So we will do this computation much more easily a bit later when we talk about the equivalent of Gauss's law for this Biot-Savart law. Okay. Maybe one example that I could do, so let's just take 2 minutes to do this one. Example 5.6, so B field above current loop. So let me try to, you know, impress you with my drawing skills that I have here. So I will have a loop. Actually, that's not a half-pad loop. The radius of this loop is going to be big R. And what I'm going to do is compute the magnetic field at a point here, which is a distance Z above the loop. Okay, so here immediately we can kind of use symmetry of the situation to understand in which way the field is pointing. So first of all, I've got a current which goes like this. So I've got this current here, I, going in this direction. And now I want to do the integral in the Biot-Savart law. So I want to do the current with the line element with the distance that I have here. Okay, so how does that go? I've got the little dl here, okay, which is just like going along the angular direction here. And my vector r minus I prime is this one here. That's the point at which I want to do it. So you see, if I have one arrow, I have the arrow pointing this way. I have this arrow pointing this way, and if I do the cross product, I get an arrow pointing like, I mean, you have to visualize it, right? It kind of comes out in this direction. So these two are not parallel, right? So this one is about this axis, and then I go like this. So this one goes out, kind of out in the other direction. But because I've got rotational symmetry, then essentially so all the contributions, if I've got my my measurement point here, got the contribution here, the dl, the r minus r prime, and then you see dl, r minus r prime, puck, puck, puck. The arrow goes like this. But then I rotate this point all around, so this arrow rotates all around. And the only thing that doesn't cancel is the vertical component of it. Okay? So if we just define some angles to this, so let's just put some angle theta in here. Then essentially yeah, so the kind of, you see, so that's the angle here. The projection, let's see, how do I want to do this to make it kind of clear? So in Biot-Savart, okay, so what I want to so the resulting B will be along Z. Okay, the total B is going to be just B times Z hat, and this field here is going to be the integral of the contributions coming from all the little segments around this circle here of the vertical projection of the cross product between this vector and this vector. Okay, so how does that look a bit? So the kind of magnitude, it becomes B is mu0 over 4 pi, and now there's an overall current which is always the same, and what I will want to do is the integral, okay, of the whole displacements that I have here. So I'm kind of integrating over this whole line here. And now, yeah, what do I have? The projection onto the z of this little vector here has this cos theta, okay? And the distance that I have here is just r squared plus z squared, okay? But this cos theta here that I have in there, this is really just r over r squared plus z squared, okay? And this whole thing does not change as I do my integral here. This projection is the same for all the angles here, so I can actually take it out of the integral, mu0 I over 4 pi. And now I've got, you know, this cos theta over r squared plus z squared. And now the integral dl prime, that thing here is just the circumference of this circle, which is just 2 pi r. Okay, so in total, I just get that this b is equal to mu0 I over 2, yeah, mu0 to 2 pi r here. And then I've got the r squared over the distance squared, r squared plus z squared to the power 3/2. Okay, so I mean, you see, we were able to do this this little integral here, just thinking about the vectors and the cross products, just because it's quite symmetric, so it's quite easy to cancel all the components that we have. Of course, if the shape of the loop was different, then the integral would look dramatically different. Okay, but that's the kind of application in which you can actually do something with Biot-Savart's law. Okay, so the magnetic field that you have coming from a loop like that, yeah, the way it looks, if you look around, you've got the current going like this. You remember the right-hand rule. There's a circulation like this everywhere. But in the middle of the axis, then, of course, the field is pointing purely up. If you move away, then it becomes more complicated. But that's not what we're calculating. Okay, so that's just a simple example application. Okay. Now, there are some important things to say about these vectors. You remember for the electrostatic field, we would characterize the electrostatic field by specifying its curl and divergence. So here we can do the same. So let's just study this bit. So the divergence and the curl of B. And then actually the easiest thing is to, or if you want the cleanest way, is just to compute it. To compute it straight from UvA. Okay, so let's do the divergence first. So we're going to have divergence of B evaluated at R. What is this? It's just going to be, I've got my mu0 over 4 pi. And now I'm going to well, maybe what I'll do is I'll first give you the volume version of the UvA. Okay, so given a J, what we have is B of R is mu0 over 4 pi. The integral over the volume that we have of just the current density. I'll write it like this. So J vector evaluated at R prime cross the R minus R prime vector divided by R minus R prime cube. Okay, so that's the general situation that we look. You know, it's like completely generic. Right, so let's just compute the divergence of that thing. So what do I get? I get that I can apply the differential operator, this divergence, inside, because there's only one place where there's an R dependence. So the div operator acts on R, not on R prime. So it doesn't touch this one here. So I can just bring it in, B tau prime over V. And now I've got the div of this whole thing here. Okay, and I'll write it out fully. Okay, so how does that go? So first thing, we can actually write that the combination R minus R prime divided by R minus R prime cube, this is, you remember the identity, is just the gradient of 1 over R minus R prime. Okay, you remember we saw that when we were discussing essentially the scalar potential for electrostatics. It's just an identity. So I can rewrite this thing as just the gradient of this scalar function, 1 over distance. Okay, that's the first thing. The second thing, there's an identity that we can use. And this identity gives us the divergence of a cross product. Okay? And this is again something that you're not expected to know by heart. It's one of these handy identities that you have in the inside cover of books or in the useful formulas at an exam. So what is this? Well, it's just B dotted into the curl of A minus A dotted into the curl of B. Okay, so that's just like a mathematical fact. and we're going to plug this into this equation here, where you know, what I'll do is I'll consider this to be A, and I'll consider this, or you know, minus Argad, to be the B. Okay, so let's just do this. Let me try to write it here. So what I mean by this is that the divergence of this J of R prime cross R minus R prime divided by R minus R prime cubed. What is this? So first of all, I use my first little identity here. So there's a minus. It's going to be the divergence of J of R prime, okay, cross the gradient of 1 over R minus R prime. Okay, so there's just 2 minutes of pain to go through, and then we'll have a glorious result. So the now we can use this this identity here, right? Noting that the divergence, you know, if I have the divergence here, it's a function of R. It's not a function of R prime. So the application of this operator on this one does nothing. There's nothing there. So you have to remember that. Okay, so what do I get? Well, I get using the identity. So I'll get minus gradient of 1 over R minus R prime dotted into the curl of J R prime. Okay, and then plus just the J of R prime, which is, I say, dotted into the curl of the gradient of 1 over R minus R prime. All right, so that's when the ugliness becomes beautiful, because this is just 0, because I'm taking derivatives with respect to R of something that does not depend on R. It depends on R prime. So nothing there. And this thing here is also equal to 0, because the curl of grad is 0. Okay, it's just an identity. A gradient has no curl. So this whole thing is just equal to 0. So what we get is just that the divergence of B is equal to 0. Okay, you see it was much less painful than you thought, at least at the end. Okay, now how do you interpret that thing? So what is the equivalent electrical field condition that we have here? You remember, if we took the divergence of the electrical field, we would get that it was just like the charge density divided by this constant epsilon 0. Okay? So it was contingent on, in the case of the electrical field, it was contingent on the existence of local charges. Okay? Point charges that would create the electrical field. Now, what does that mean here? Essentially, what we're stating is that, at least as far as magnetostatics are concerned, we'll get back to dynamics later, at least in the static case, there are no magnetic charges. Okay? So, conclusion, no magnetic charges. Okay? So no monopoles in particular. Okay? Because if we had monopoles, we'd have like local charge density for magnetic units, but we don't have that. It never, ever, ever happens that there's a divergence of the field. If you look at any enclosed volume of space, out of that thing, the total flow is just 0. It integrates to 0. Okay? So that's the kind of important equation that that you have here. Okay, and I see that time is going fast. So what we could do is already take a little break and then carry on after. because we just have to do another identity now for the curl. It's a very similar kind of reasoning, and then we'll get the other equation that we want, which is Ampere's law. Okay? So yeah, just take a little bit, and then we carry on.